Much, Horacio, and thanks to the organizers for putting this amazing workshop. It's a pleasure to be in Natal. We had an extremely great time last week, and I'm sure this week we'll also have a lot of fun. Okay, so today I'd like to tell you about relatively recent work, which was done in collaboration with Javier Magan, who's here, and with Brian Swingle, who's in Brandeis. And everything that I'm going to talk about is going to be based on these two papers that appeared over the last couple of months. So by the way, please interrupt me during my talk if you have any questions. In order to set up the motivation, let me start by saying that there are two ideas in holography which appear to be in some tension with each other. One of them is known as ER equals EPR. It's famously known as ER equals EPR, and says that enough microscopic entanglement between two quantum systems generates some notion of a connected emergent space. Okay? This is, of course, best understood for quantum systems that describe black holes, in which case the emergent connected space is essentially the black hole interior. Okay? So the classic example where this can be really well understood is that of the thermofield double state of two holographic CFTs, which is this very particular entangled state. Okay? So essentially the thermofield double is the canonical purification of the thermal state on one of the two CFTs. So it is a highly entangled state at high temperatures for the CFTs, but it is very particular. Okay? So the thermofield double is known to be holographically dual to the eternal black hole in ADS. More precisely, the semiclassical dual lives on some bulk time slice, which I'm depicting in the dashed lines here. And this bulk time slice contains the information about the initial data of the spacetime at the classical level, but moreover, it also contains the initial state of the quantum fields. So for the thermofield double, this state of the quantum fields is essentially the Hartle-Hawkins state. Okay? So in this case, ER equals EPR is sort of manifest because the thermofield double is a highly entangled state, and on the other hand, in the bulk description, the semiclassical state lives on a connected space, joining the two asymptotically ADS regions. Okay? The second idea, which is sort of in tension with this one, is that this example that I just told you about is very fine-tuned. It's non-generic. Okay? And in principle, the idea is that in these situations, or situations made out of collapse, so a black hole made of collapse, perhaps you can also let it evaporate and so on. Those situations might actually have an interior, but they are not a generic example of ER equals EPR because they are not generic entangled states. Okay? And this was discussed in the early discussions in black hole evaporation, but it was made very precise in a paper by Don Polchinski in 2013. So the question that I want to try to understand today is whether ER equals EPR is generic or not. Okay? In principle, trying to understand this question in a generic quantum system is very difficult, so I will just focus on systems describing black holes. So the question then becomes whether typical EPRs of two black holes, typical entangled states of two black holes, have Einstein-Rosen bridges associated to them or not. Okay? So in order to understand the general argument by Don and Joe, let's just first try to define what we mean by typical EPR. Okay? So let's start with the simplest system, which is a collection of n qubits, and let's place the system at infinite temperature. So let's just forget about finite temperature effects for now. Here I'm plotting, okay, so let's just consider two such systems, and among all possible states between these two systems, let's consider the collection of maximally entangled states. So I'm denoting this set of maximally entangled states between the two systems of qubits by EPR here. So the thermofield double at infinite temperature is one such state, is a point in this set, and it has this particular wave function. Here I represents the energy eigenstate of some Hamiltonian that is given to me, that is defined in these systems in order to define the thermofield double. Okay? a typical EPR is essentially a generic point in this set. Okay. So how to reach a generic point? Well, we can just take the term of field double and apply to it some random unitary on one of the two systems. In this case, the right system. This will land me in a generic point in this set. Okay. Of course, the notion of generic needs to be associated to a notion of measure. Here I'm using the measure in the set of maximally entangled states, which is inherited from the hard measure in the space of unitaries. Okay? So a generic or a typical EPR can actually be diagonalized. So essentially by diagonalizing the unitary which creates the typical EPR, we can bring the wave function of the state to this form. Here, so this is essentially how to diagonalize the unitary and write it in the form of a two-sided state instead. Okay. So the phi's here, they are just eigenvectors of the unitary UR, and these phases that define the wave function of the typical EPR are just the eigenphases of the random unitary. So an analogous way of defining a typical EPR is to determine a statistical distribution of eigenphases and of eigenvectors in this form. And in particular, for a typical EPR, the eigenvectors here are uniform random states. And the eigenphases are distributed in a very particular way. Particularly, their distribution is given by the so-called circular unitary ensemble, which is the distribution of phases of a hard random unitary. Okay. So for us, the most important property of these phases is that they will be statistically correlated to repel each other. So nearby eigenphases will be statistically correlated in a random unitary or in a typical EPR to repel each other. One can see this empirically just by plotting, by taking a very large random unitary and diagonalizing it and plotting the distribution of phases. On the right-hand side, I'm just plotting the histogram of the eigenphase separations between nearby phases in this distribution. And as you see, the distribution is a Wigner-Dyson-like distribution where small eigenphase separations are statistically very unlikely. So the main argument is that, the main argument in this paper, well, one of the arguments in that paper, is that typical EPRs have the same entanglement spectrum as the term of field double. So as far as entanglement goes, they are equivalent to the term of field double. But the structure of correlations in these states is very different. In particular, simple operators have very small correlations between the two systems in typical EPRs. And the signal, say for a left-right two-point function, is very erratically dependent on the actual microstate, on the actual instance of the ensemble of states. So this was used in the past to argue that this signal cannot be reproduced semiclassically. Okay? And therefore, yeah.
Well, I thought we said it can't be reproduced semiclassically by short wormholes.
Right. Okay, maybe, yeah, thanks for the comment. Maybe you will agree with my talk, I don't know. But yeah. Okay. Yeah, in principle, okay, the fact that this signal is exponentially small, it's already telling you that if a wormhole exists, it has to be of certain length or larger. But it's not obvious whether, you know, this erraticity can be incorporated from the semi-classical bulk picture in terms of matter fields and so on, at least as far as I understood.
Sorry, so small correlations means long.
Sorry?
Long wormholes, right? Small correlations means
long wormholes. Yeah, this was Don's comment. Yeah.
Yeah, just a small comment. So implicitly, at least, you're assuming that you've already pre-designed a set of simple operators in each of your system.
Yes.
Because a priori, a state doesn't have by itself physical properties without already telling you which observables I can use.
Yeah.
Because I could always conjugate my observables via U and be back to where I was before.
Yeah, I'm assuming that you're given some few-body Hamiltonian in the system. Then you're defining the infinite temperature term of field with respect to that Hamiltonian.
It's two Hamiltonians.
Yeah, it's
you
the
need to have
same.
the two systems, and you need to have an identification between operators on both sides.
Right. I'm using the same Hamiltonian on both systems.
And an exact time equivalence. So the two systems have exactly the same clock.
Right. They have the same Hamiltonian, but they have their own time in principle.
But in order to have the thermophile double, they need exactly the same time, and also your operators have a time relation.
Right. So this is a particular state which is annihilated by h left minus h right.
And with a particular assignment of observables.
Right. I would say the observables are just local operators in the system.
But they could be time-evolved local operators, and then I can still make the state the same.
Well, but the time-evolved ones, if you have a few body Hamiltonian, start to become completely non-local.
For a given set of observables.
Right.
You're
Yeah.
assuming also some anti-unitary operator, particular
Some anti-unitary operator.
the CPT conjugation.
Correct.
Right. Yeah, okay, so maybe, yeah, I'm assuming that these two systems are related in a particular way, but by this thermophile double, perhaps also by the choice of algebras. I'm not sure about that, but yeah, okay. So in today's talk, I will try to argue that one can explicitly construct families of Einstein-Rosen bridges that incorporate this erraticity semiclassically, and the wormholes in question will be called Einstein-Rosen caterpillars for obvious reasons. So the geometry of the wormhole is essentially a long cylinder, which is supported by a large number of matter inhomogeneities. Okay? And the two length scales which characterize the coarse grain geometry of the caterpillar are its total length, L, and the length scale of matter inhomogeneity is L delta. Okay? So I will essentially build ensembles of caterpillars with the same coarse grain features, but with different individual realizations or with different distributions of matter that in principle are thought to reproduce this kind of signal. Also, they could reproduce this signal, okay? So in the second part of my talk, I will in fact use the gravitational path integral to show that the ensemble of caterpillars of a given length, their corresponding CFT microstates, are close to typical EPRs, okay? So I will derive a quantitative correspondence between the length of the caterpillars and the amount of microscopic quantum randomness of the ensemble of states. So the longer the caterpillars, the closer to a typical EPRs we can get. Okay, so the plan is to start from the thermophile double state, which is a state which we understand from the gravity side, and try to reach a generic point in Hilbert space from there. Okay. So the first option is to just take the thermophile double and time evolve it with a time-independent Hamiltonian. And one reaches states which look like this. They're just e to the minus ITHR times the thermophile double. Here I'm just focusing on the example of the system of qubits at infinite temperature. So this kind of state looks like this. When diagonalizing the energy basis, it looks like this. It has a collection of phases. And it has some eigenvectors, which are the energy eigenvectors associated to the Hamiltonian. Okay? Now the point is that this evolution will never explore generic points in Hilbert space. The reason is that the evolution is constrained to a measure zero subset from the conservation of energy. So the conservation of the Hamiltonian along the trajectory prevents the state vector of exploring most of the set of maximally entangled states. And this is obvious in this form where if the Hamiltonian is few body, the energy eigenstates of a few body Hamiltonian are not random states. So the distribution of eigenvectors in which the wave function looks diagonal is different from the one of a typical EPR. But moreover, even if we choose a completely random Hamiltonian where the eigenvectors are random states, the distribution of phases is never typical. And one way to see this is that the distribution of phases for a time-independent Hamiltonian is never able to incorporate the characteristic eigenphase repulsion that I told you about in a few slides ago. Okay? So the way to see this empirically is just to take a completely random Hamiltonian and to just plot e to the minus ith diagonalize the time evolution operator for very, very long times. Times of order of the inverse mean level spacing, so these are times which are exponential in the system size. And just take the, plot the distribution of phases for this operator. The difference is essentially that these phases are, tend to clamp on top of each other. And the reason is that they are statistically uncorrelated with each other. So this is very transparently shown in the right picture, where I'm just plotting the distribution of eigenphase separations again, and you see that this distribution follows a Poisson-like distribution. Okay. So nevertheless, for black holes, the Hamiltonian evolution allows to create more general examples of ER equals EPR. And the idea is that by just time evolving the thermofield double upwards, this just creates a wormhole which includes parts of the interior now, and so the wormhole becomes longer and longer. So a more generic EPR, a more generic ER, sorry, has a longer wormhole, okay, from this sort of particular argument. Now, this picture led to the idea that this wormhole in the interior emerges as some sort of quantum circuit associated to the time evolution operator. And the length of the wormhole parameterizes the circuit depth, while its volume represents some notion of circuit size. And this has led to several conjectures regarding the volume of this wormhole and some notion of quantum complexity of time evolution. So, but I want to emphasize that even if we just take this setup and restrict to exponentially long times, so at Heisenberg times, the state becomes very, very complex. So in any reasonable, with any reasonable notion of quantum complexity, preparing the time-evolved thermofield double will be very hard. However, the state is very atypical. So among all of the entangled states of these two black holes, this state is never typical. Okay. And yeah, I should mention that understanding what happens at exponentially long times, even in this setup, is a very interesting open problem that people have started to think about. Okay, so what we will do today is to instead consider time-dependent Hamiltonians driving the evolution. So we will consider time evolution operators associated to these time-dependent Hamiltonians. So this T is just the time ordering exponential. And in our case, it will be convenient to choose Brownian Hamiltonians, which consist of a set of operators, O alpha, which we can think of them as being few body operators, and a set of couplings, time-dependent couplings for each operator. And so the total Hamiltonian is just the sum of a bunch of operators with these time-dependent couplings. Okay. Now we will choose these couplings from a collection of random couplings, which are distributed according to white noise correlated distribution. So what this means essentially is that these couplings are time dependent and very erratic at each time step. The average value of the coupling at each time is 0, and the 2-point correlation is ultra local in time. This means that the couplings at different times are uncorrelated with each other. And the sort of heuristic picture to have in mind is that if we just apply this time evolution operator to the infinite temperature thermofield double, the trajectory of the state will follow a sort of a Brownian motion in this space. And so we can define ensembles of states at fixed time by changing the couplings of the Hamiltonian. So we will have different Hamiltonians corresponding to different instances of the couplings, and therefore different unitaries. At fixed time, we can define an ensemble of states this way. And so the distribution of states that defines this ensemble will spread diffusively, given that this is a sort of a Markov process in this space. Okay, and the endpoint of this spreading will be to reach a homogeneous distribution in this set, which is why the state psi of t eventually will become a typical EPR. And this kind of system is interesting because the dynamics is the continuous version analog of a random quantum circuit. So a random quantum circuit is a discrete time model where at each time step of the circuit one chooses the Hamiltonian or some unitary gates at random from some ensemble of gates. Here what we are doing is choosing Hamiltonian at random at each time step, and just time evolving the system with an infinitesimal unitary, which is e to the minus I delta t h at that particular time step. Okay. So let me just show you the advantage of using this kind of system. The advantage is essentially that one can solve for the average dynamics exactly. So let's consider, as an example, the spectrum form factor of u of t. One could also consider correlation functions and so on, but let's consider simpler quantity. So the spectral form factor is just the trace of u of t square average over couplings. Okay. Pictorially, the spectral form factor contains two traces. So there's two contours here. Each contour represents this one trace of u of t, this one trace of u of t star. And the wiggles represent the time-dependent couplings that define the Hamiltonian. And we're just taking the average over couplings here. The advantage of using white noise correlated couplings is that one can rewrite this average exactly as an effective thermal partition function for some effective Hamiltonian coupling the two contours. So T in this effective description plays the role of an inverse temperature. Okay? The idea physically is that these couplings are uncorrelated at different times, and so the average over couplings can be exponentiated exactly, and one finds bilocal interactions between the two contours in the form of a time-independent Hamiltonian. So the Hamiltonian looks like this, essentially. It's just the sum over the operators of the first operator acting on the first contour minus the second operator acting on the second contour square. So the fact that this is a square means that there is a double trace kind of coupling between the two contours. Okay. Now the advantage is that one can just evaluate the spectrum form factor exactly, but just focusing on the eigenvalues and so on of the effective Hamiltonian. At very late times, only the ground space of the effective Hamiltonian contributes, with perhaps a small correction coming from the first excited states. And so the nice thing about this effective Hamiltonian is that under very general conditions over the O alphas, the effective Hamiltonian only contains one ground state. There's a unique ground state, which is the infinite temperature thermofield double. Okay, and moreover, one can show that the effective Hamiltonian is gapped, even if the system admits some sort of thermodynamic limit. Okay, so just evaluating these two the contributions in this trace, so one gets a factor of 1 coming from the ground state to the spectral form factor, and a small exponentially decaying contribution coming from the first excited states. Okay. So another nice thing is that for large systems which admit semiclassical descriptions, one can show that this kind of contribution is reproduced by an on-shell saddle point, which is connected between the two contours. So here we started with a disordered Hamiltonian, which was time dependent between the two systems. By taking the average over couplings, we created effective interactions between two contours. And for large systems like those in gravity, this kind of contribution supports an on-shell wormhole contributing to this quantity. Okay. Okay. So, but I just wanted to show this example to illustrate that this unit value of the spectral form factor signals that the Brownian Hamiltonians will eventually generate random unitaries, while time-independent Hamiltonians will not. And the idea is to just compare the spectral form factor for the Brownian system, which has this form, in red, to the spectrum form factor for an ensemble of time-independent Hamiltonians, which is here plotted in black. So this unit value at very late times is essentially the value of this plateau. And what I want you to notice is that this plateau is very different from the one for a time-independent Hamiltonian. So this difference is essentially exponentially large in the system size. Here I'm just plotting the two plots for 7 qubits. And essentially this difference is what signals that Brownian Hamiltonians are able to generate the eigenphase correlations of a high random unitary, whereas time-independent Hamiltonians are not able to do that. Okay, so the value of the plateau here exponentially larger than the one for the Brownian system signals that the eigenphases of e to the minus ith are Poisson distributed, whereas here the eigenphases of the unitary are distributed according to the CUE, at least up to the second moment. Again, this happens because under very generic conditions for the operators, the Markov process, which defines the Brownian Hamiltonian, produces a dense exploration of the space of unitaries. And the state psi of t generated this way eventually becomes a typical EPR. Okay, questions up to this point? Okay, so,
Sorry, just one quick question. I mean, just concerning the setup of using Brownian motion there, I mean, this sounds like something very arbitrary, but of course there's a symmetry which is generated by this time evolution. I mean, can you just somehow incorporate this into the Brownian motion, or is this, do you ignore it? I mean,
what symmetry?
Just the time evolution e to the iht.
Right. Yeah, you could incorporate it to, so you could start from a sort of unperturbed Hamiltonian h naught, and just add this as a perturbation. You would find a different effective Hamiltonian, which in particular is not Hermitian. So there is some part of the, so you see that here we are reducing some Lorentzian evolution after averaging to an Euclidean problem. And so if you do that, if you add the h naught for the as some sort of bare Hamiltonian, then you would find a contribution which is still Lorentzian to this effective Hamiltonian. And so the problem becomes a little bit more complicated, but you could do that, yeah. Thank you. Okay. So the goal is now to apply this discussion to black holes. Okay. The first problem is that for black holes, one starts with a finite temperature thermofield level. And just applying this random circuit, U of t, on the right-hand side of the black hole, this random circuit will eventually, well, it will increase the energy of the black hole because it's just, you know, perturbing stuff here. And eventually the black hole will become out of equilibrium and we will lose track of the black hole that we started with. I forgot to say that for this kind of system, we choose the drive operators to be operators associated to back matter fields. So we're thinking on an ADS-CFT setup where the O alphas are just low conformal dimension primaries. And so what these time-dependent couplings do is that they just excite non-normalizable boundary conditions for certain bulk fields. Okay, so this way you can easily see that doing this time evolution will insert energy into the black hole, and eventually the black hole will go out of equilibrium. And we are interested in a situation where the number of drive operators of the circuit is very, very large. And so one can see that this kind of construction has a limitation where one is only able to apply the random circuit for a maximum amount of time, which in units of this coupling J is related to the mass of the original black hole divided by the number of perturbations times the energy of each perturbation. Okay, so if we choose the energy of each perturbation to be thermal, so we are essentially exciting degrees of freedom of the Hawking atmosphere of the black hole. This is essentially the entropy of the black hole divided by the number of perturbations. So if we want to actually perturb a large number of fields here, this ratio is actually very small. It's of order c to the 0, where c is just the central charge of the CFT. And so this is a standard problem of trying to apply these things to finite temperature systems. So what we did in the paper was to include, well, first of all, define a canonical version of a random circuit by gradually cooling the system down while implementing this time-dependent unitary evolution. So essentially, the operator that we define is now not unitary. It includes parts of the Euclidean evolution, which essentially cool the state down. So initially, we implement an infinitesimal version of the random circuit. This will increase the energy by a little bit. We then cool the system down with small Euclidean evolution with some bare Hamiltonian, and we do this repeatedly in such a way that this operator will be able to maintain the system in equilibrium at all times. Okay. And we take the infinitesimal time step of Lorentzian evolution and the infinitesimal time step of Euclidean evolution to 0 while keeping the ratio fixed. Okay? And the total time is also fixed. Now, formally, this operator can be defined by path ordering along some complex time contour of the CFT. And so here I'm just representing this contour. The vertical directions just represent the directions of cooling, where the Euclidean time evolution is implemented. The horizontal directions just represent the directions of Lorentzian evolution. And the fact that there's time folds in this contour is just technical. It is essentially, as Joanna was asking, because for a black hole we actually are given some bare Hamiltonian, and we're just perturbing this Hamiltonian with the Brownian perturbations. So we just want to isolate these Brownian perturbations. And so the forward evolution is done with the total Hamiltonian, while the backwards evolution is done with the bare Hamiltonian in such a way that each timefold effectively implements the interaction Hamiltonian. We're just isolating that part. And the idea is to use this kind of operator. Yeah, was there?
Martin, I just understand. Is the Lorentzian part of time evolution important for your construction, or could you just equally well apply some operator at zero Lorentzian time?
That's a really good question. We could, in principle, define some operator, like let's say an operator which creates a shell or something. Yeah. We could just implement, create states which contain a bunch of shells in the black hole interior. The problem with that is that we don't have any microscopic control over what the operators are in the CFT. There's this issue with shells that, well, they are composed of a large number of primaries, and you never know whether what you're doing is just an input from the bulk point of view. But as Alex was saying in his talk, it would be nice to have like a CFT derivation of what you're doing. For this class of operator, for this class of small unitaries, you can actually do the calculation in the CFT and compare. Yeah, but in principle, I mean, we are not restricted to do this. You could do whatever you want.
But instead of shells, you couldn't use just sources for some low dimension operator in the bulk. Still at s equals 0.
The problem with that's a good point. The point is that after averaging over couplings, all of these Lorentzian evolutions will disappear, and effectively the problem will reduce to what you're saying, which is just the problem of turning on some couplings for some operators. But the origin of this, the origin of where this problem will come from is essentially this one. Is from the fact that we're defining some small Lorentzian time evolution here, we're just taking the average over the time-dependent couplings. But yeah, in principle, you could do other things. The construction could be more general. Thanks. Yeah.
So, suppose in gravity the probe operators are just a very restricted set of operators. When you say U like this, you just take one of these operators, maybe exponentiated with some e to the I epsilon times the probe operators, or you still allow U's to be general? Because
you mean
the time behavior would be very different, I think, between
you mean the choices of the operators of alpha?
Yeah, the ones that sit in U. Yeah, these. So K scales like n squared. So I allow all operator or just n. Good. Is it single trace operators, which there are few, or generic operators?
Okay, the point is that they need not be independent conformal primaries. So they could be the same primary applied at different points on the sphere, and then you assign a different time-dependent coupling to each of them, and you vary it, and you choose the ensemble of couplings in such a way that these couplings are uncorrelated for different points. Okay?
But still, I mean, is it just gravity modes or polynomials of single trace, or full n squared?
No, you could do it with single trace operators. This is what I'm saying.
But then there are relatively few operators like this compared to the dimension of the Hilbert space. So
there are few primaries, but you can use their descendants, or in other words, you can apply the primary at different points.
Okay, but do you allow black hole operators in these?
No. They're just
Okay.
matter, low energy matter operators that we want to just perturb.
Okay, so they are fairly dilute in the space of all operators in the theory.
They are, it's true, but you can build high energy objects with low energy quanta, right?
Yeah, but you need, it's a very complicated task. You need of order n to some positive power of those.
That's what we want here.
N scale. So whether the O's are generic or sparse will show up in the behavior of the CU as a function of n, like the time scale that will go in. Okay.
Yeah. Okay, so yeah, we're building this kind of state by applying this operator in the Euclidean past, and the intuitive idea is that this will excite boundary conditions for some low energy matter fields. And the difference with the picture before is that these excitations will actually propagate in the Euclidean manifold, and they will appear directly in the black hole interior. So as opposed to this case, we won't need to insert them from outside, but they will actually appear directly in the black hole interior, and this is what will allow to keep the black hole in equilibrium for much longer times. Okay, so these are the states. We just want to find the semiclassical duals to the states, and the idea is to use the standard ADS-CFT dictionary, where one writes the norm of a state. In this case, the norm of a state is given by this contour. So this is the ket and this is the bra. And the rule is to use the gravitational path integral to fill in the bulk given these boundary conditions. So the boundary conditions are such that here we have time-dependent couplings associated to sources for matter fields. We just have those in the bulk as boundary conditions for non-normalizable modes of bulk fields. Of course, trying to find a saddle point of this situation is extremely complicated. So a technical simplification that we will do is just to take the average over couplings. Okay. So we just average over the couplings here. We reduce the problem of computing the norm of an individual instance to computing the average norm over the ensemble of states. And this has two simplifications. The first one is that this reduces to a time-independent Hamiltonian problem. So we're just computing the survival amplitude of the thermofield double given this Euclidean time evolution. And the second simplification is that this problem is purely Euclidean. So it doesn't have any Lorentzian part after averaging over couplings. Okay? So the effective Hamiltonian in this case is a finite temperature version of the effective Hamiltonian that I told you about for the infinite temperature case. And it turns out that it takes the form of a generalized Maldacena-Chi Hamiltonian. Okay? The Maldacena-Chi Hamiltonian was essentially a Hamiltonian which was proposed in this paper in 2018 to essentially construct systems that whose ground state look like the thermofield double state. So in this case, the Hamiltonian consists of the bare Hamiltonians on the two systems, 1 and 1 prime, 1 and 1 bar. And then there is these double trace-like interactions between the two systems. So the additional term for it to be finite temperature is this bare Hamiltonian term. And the lesson from these papers is that for a large number of perturbations, the effective Hamiltonian is gapped and it contains a unique ground state. And the ground state of this effective Hamiltonian looks similar to a thermofield double. So for holographic systems, this kind of effective Hamiltonian allows to support eternal traversable wormholes between two systems. Okay? We will use this kind of information to generally extract information about the average geometry over the ensemble of caterpillars. So the idea is very simple. The idea is that we are just computing the average norm of the ensemble at the disk level. And the point is that we wrote this disk computation in terms of the survival amplitude of the thermofield double given this Euclidean evolution. So if T is sufficiently large, this Euclidean evolution will effectively work as a projector into the ground state of the effective Hamiltonian. And so one can show that if T is very large, and if the effective Hamiltonian admits a ground state which is similar to a thermofield double, then there will be an effective isometry of the disk, and the disk will become very, very long. Okay, so geometrically, the geometry in the middle here, in the bulk, it will be very similar to that of an eternal traversable wormhole. This is a sort of general argument that I'm giving because this construction could, in principle, work in higher dimensions. Okay? But in 2 dimensions, one can actually solve the problem exactly using the technology developed by Malacen and Chi. So the idea is that, well, in this case, the geometry of the disk saddle is just hyperbolic space, H2. And the only degree of freedom is this length degree of freedom that Thomas introduced in his talk. And so this is the, Liouville particle mechanics. I'm just talking about the classical theory. This is just Liouville particle mechanics of this L variable. And what these interactions between the two contours coming from fermions do is to add this additional term which stabilize this length. So essentially this potential admits bound states after the interaction is turned on. And so one can construct this solution in JT gravity as a bounce of this length classical mechanics problem. So what this argument tells us is that there is some effective isometry, approximate isometry, coming from the fact that this effective Hamiltonian is preparing the ground state at each time slice, at each blue time slice. And so the actual semi-classical dual to the states is prepared on the red time slice. And so the red time slice includes some approximate isometry in this tau direction. Okay, so essentially by analytically continuing this saddle point, one ends up with a very long two-sided black hole solution supported by some matter, some average matter here. And the main conclusion that we want to draw from this analysis is that the length of the wormhole will grow linearly with the circuit time used to prepare the states. Okay. So this shows that the coarse-grained geometry of the ensemble of caterpillars is a long cylindrical wormhole supported by matter. One can find a more precise relation by studying the matter inhomogeneities on top of this average stress energy tensor. This will be given by the first excited states of the effective Hamiltonian, which have a gap and some bulk length scale, and one is able to find a linear relation similar to the one that I was representing before, but just fixing all the proportionality constants. So essentially the length of the caterpillar in units of the matter correlation scale is given by the boundary circuit time t in units of the, boundary total time t in units of the boundary circuit time, which is the inverse of the gap of the effective Hamiltonian. Okay, this was the geometry part of the talk. Any questions up to this point? Okay, let me just, by the way, I don't know how I'm doing with time. How much time do I have? Okay, great. So that was the geometry part of the caterpillars. We found that, yeah.
The claim is that this is the generic state of a wormhole with this length?
No, the claim...
Or these are just examples of wormholes with this length?
So the claim will be that this ensemble of states is k copy indistinguishable from the typical EPRs for some k, which depends on L. So any k copy quantity that you measure in this ensemble of states, if you just average over the ensemble, so k equals 1 is just some correlation function. Okay. If you average over the ensemble, the signal will be the same as for the typical EPRs. But in principle, you need k to be exponentially large in order to actually say that these states are typical EPRs. And so that regime is sort of out of semi-classical control for obvious reasons. Yeah.
So when you say if you average over the ensemble, then you're turning your entangled state into a density matrix. Is that correct?
Right. So there will be, great. There will be an average mixed state.
Correct.
Determining the properties of the average. Yeah. Okay. Yeah, exactly. Okay. So more questions? No. Okay. This relates, what Herman just asked relates to what I was going to say here. So the point is that at small times, the ensemble of caterpillars is distinguishable from the typical EPRs. And the way to distinguish them is to just measure any 2K copy quantity and compare the average value of this 2K copy quantity to the same quantity for the typical EPRs. So for k equals 1, we would just measure the expectation value of some state-independent operator. Just take the average of this thing. What Herman was saying is that this is equivalent to taking the trace over a mixed state, which has all the information about the average over the ensemble, times this operator. Okay? But the point is that we want to compare this quantity to the one for the ensemble of typical EPRs. And in principle, we want to compare these two quantities for any operator. So in quantum information, a quantum state K design is an ensemble of states which is statistically K copy indistinguishable from the typical EPRs. So for K equals 1, the statement would be that these two quantities for a K design are the same for any operator. For K equals 2, we would have the same expectation values of state-independent operators. We will also have the same variances of state-independent operators, but we will also have nonlinear quantities over the state, like the second Renyi entropy of the reduced density matrix to one of the two sides. This quantity, on average, it will be the same as for the typical EPRs. So physically, to have a 2 design or a 3 design is already a very strong requirement. And it turns out that in Brownian systems at infinite temperature, this Brownian time evolution typically forms a K design very efficiently. And in particular, the time that it takes to form a K design asymptotically grows linearly in K. Okay? And in fact, this linear growth is very universal, and it is independent of the details or degree of locality of the operators that define the Brownian Hamiltonian. So we want to show that this linear growth is also true in gravity. So what we will do is to compute the distance between our ensemble and a K design. So the way to do that is a little bit convoluted. I would need to introduce some quantum information definitions. But for this talk, let's just assume that this distance is given by the difference between two quantities, which are known as the frame potentials. So the frame potential over the ensemble is essentially taking two independent instances of the ensemble, just taking the overlap between the two, taking the 2kth power of this overlap, and just taking the average of this thing. Okay? If this quantity is equal to the infinite time value, then we have formed an exact quantum state K design. If the distance is small up to some resolution, we have formed an approximate quantum state K design. The advantage of this is that in gravity we can compute these overlaps using the gravitational path integral. So the way to do that is that for, let's say, K equals 1, we want to see how long it takes for our ensemble of caterpillars to form a 1 design. We would need to take the overlap between two instances of the ensemble, so this is the ket and this is the bra, for different couplings. We would need to take two copies of this thing. We would need to evaluate the average over couplings of this replica computation to replica computation using the gravitational path integral. So I won't go into details, but the same trick that worked for the norm works for this kind of quantity, for this 2K replica quantity. And the idea is that this frame potential is a thermal partition function for a 2K replica effective Hamiltonian. So now this effective Hamiltonian will couple the 2K replicas, in this case the two replicas together. And the role of time is again an inverse temperature. So this is a thermal partition function at inverse temperature 2T. And the main point that we made in this paper is that at very late times, the ground space of this effective Hamiltonian breaks replica symmetry, and it corresponds essentially to the ground space of the two replica effective Hamiltonian. So all the physics of computing these 2K replica quantities reduces effectively to a two replica computation, which can be very easily evaluated in gravity. So in particular, this two replica wormhole is what controls the very late time value of the frame potential. Okay? And again, one finds a value for the frame potential, which is the infinite value. This one comes from the contribution coming from the ground state. So when all of the excited states of the effective Hamiltonian have relaxed to 0. And then there is some small correction coming from the first excited states. But the main point that I wanted to make here is that, well, since all the 2K replica computation has reduced to a 2 replica computation, all the energy scales appearing in this problem are the same ones as the energy scales appearing in the norm of the caterpillars. And so one can show using gravity that the time to form a K design grows linearly in K with a slope precisely given by the inverse gap of the effective Hamiltonian. So at infinite temperature, this is essentially J. E gap is J, which is what defines the size of the Brownian couplings. Is just the only energy scale in the problem. At finite temperature, this depends on other scales. So it depends on it's typically of the order of the temperature of the system. But the point is that since this scale is the same as the one appearing in the previous relation that I showed here, relating the length, the geometric length and the circuit time, this is also linear growth. And so we can conclude the main conclusion of the paper, which is that combining this linear growth of the amount of randomness to the linear growth of the length of the caterpillars, we can reach the conclusion that the ensemble of caterpillars of length L and matter correlation scale L delta forms an approximate quantum state K design for a K which is of the order of the length of the caterpillar in units of L delta. So on the left hand side, this represents a microscopic notion of quantum randomness of the ensemble of states, how random the states look. On the right hand side, this represents a geometric property of the black hole interior. Okay? Yeah, let me just, I forgot to mention this. Like these wormholes that I drew here in JT gravity, they can be, again, computed very explicitly. They correspond to a stabilized version of the double trumpet. So these double trace interactions between boundaries, they stabilize the length of the geodesic in the double trumpet. And one can map this problem, the problem of finding this profile, to the problem of finding a trajectory in some effective potential in classical mechanics. Okay, any questions before I jump into the discussion? Okay, let me just, yeah.
K. How exactly does that enter? Does that enter anywhere in any of these equations?
Yes, it enters. Like, let's say we focus on this JT gravity case. K being large essentially means that these operators are able to back react at leading order in the geometry, and so they modify the naive potential that you would find at leading order, and so they stabilize the wormhole classically. Otherwise, if K is small, this is not a classical effect, and you would need to like work out perhaps like quantum corrections and so on. But everything we did was classical, and for that you need a large number of order 1 energy operators.
Right, but I'm trying to understand whether the individual constituents of this ensemble are all semi-classical or not. And if you put K operators in AJCFT and K scales like say n squared or something,
right?
That's not a weakly coupled problem.
It's not a weakly coupled problem.
And it will back react, but what will guarantee that the solution is semi-classical? Because you have n squared delta function insertions.
Right.
It's not obvious that this is a semi-classical thing, right?
Right, yeah, a priori it's not obvious. What I would say is that, well, you're using low energy quanta.
But you're doing a strongly coupled computation, right? Because
yeah, I agree.
Squared of
I agree that from the CFT correlation functions do not factorize a leading order in large n and so on. But at the level of the bulk, you're just describing some heavy object which is made of low energy quanta. In this case, it's just a bunch of fields, which are each of which is low energy. In principle, you could worry about, I don't know, singularities forming in the Euclidean section and so on. We think that this is not what happens for the reason that when we compute the average norm, everything seems smooth, and the norm is self-averaging over the ensemble. So anything that you do for a single realization cannot depart by a large amount from this average geometry. This is why the caterpillar is just the average distribution of matter here and some small inhomogeneities on top of that.
So it could have a very tiny region with a very large curvature that would average out or something. So
it could be, yeah. It's not a proof. I agree that this is an interesting open problem. Yeah. Thank you. Okay, so let me just end with some discussion. Well, we've shown that the ensembles of caterpillars provide a window into the generic structure of the Hilbert space of black holes in any theory which contains, well, gravity, of course, and low energy matter. And yeah, as a future direction, it's interesting to mention that this caterpillar serves to circumvent several issues with the state counting derivation of black hole entropy using the gravitational path integral. And I will not, not explain what I mean here more. So I encourage you to go see Enzo's poster tomorrow, where he will explain this and ask him. But yeah, this is some work in progress with Enzo Bávaro, Javier Magán, Leandro Martinez, and me. Another comment which I find interesting is that the matter that forms the caterpillar lives in the black hole interior and eventually falls into the singularity. So in principle, this kind of construction allows to characterize generic singularities from their corresponding generic CFT microscopics. And it will be very interesting to relate this construction to the semiclassical or classical construction of generic singularities given by BKL. Another interesting comment is whether we can form K-designs in other ways. So a K-design is not a unique thing. You can form K-designs in many different ways. One such way could be by using measurements. So for instance, starting from the thermofield double and just performing some high energy measurement on the left system. This was studied in these really nice papers by Maldacena Corcolu and Jan and friends. And the idea in these cases is that in principle, the bulk semiclassical dual contains some end of the warp brane associated to the measurement. And it will be interesting to see whether these kind of ensembles also form K-designs or whether they are less random than the caterpillars. And at a technical level, it would be interesting to understand our construction better in higher dimensions using a specific set of operators. And as I said, at least the average problem, after averaging over couplings, is equivalent to constructing eternal traversal wormholes in higher dimensions. Some steps in this direction have been given in this paper, where they essentially use Wilson line operators between the two boundaries to support the necessary negative energy for this class of Hamiltonian to have a connected ground state. This is all. Thank you.
Thank you, Martin. Some other question?
All right. I feel like I should make a very brief comment that, since you mentioned this paper with Joe at the very beginning, that I think the primary argument in that paper was something that was completely different based on using a maximally mixed state to describe what happens for generic states. But leaving that aside, looking at this comment about trying to understand, trying to geometrize the notion of a generic entangled CFT state. Of course, there's been a long history of discussion of that. Schinker and Stanford, talked about that also in terms of long wormholes. And there, when one talks about whether it's a semi-classical discussion, or semi-classical description, the discussion usually focuses on the fact that, as in your case, to get a truly generic state, you need the wormhole to be very long. Mm-hmm. And in your case, if you wanted the wormhole to be long enough that the two-point function you mentioned originally really behaves erratically at the scale you'd like, I'm assuming you need the wormhole to be exponentially long.
No, I don't think so. You need it to be the length to be proportional to the entropy, right? So that the two-point function of a heavy
maybe it's the entropy. Okay.
Yeah,
yes. Yeah. Great. But the question is then, so at finite G, the question is that really semi-classical? You might think that what you're seeing there as G goes to 0 is an infinitely long wormhole, and that in modern language, it would be like the throat of an extreme black hole where we know there are strongly coupled modes, even though the system is broadly speaking semi-classical, and there would be important effects.
Right.
So do you have a comment about that?
No, I don't have a comment. So what I would say is that it would be interesting to actually take this state and compute the two-point function left-right, and see whether the so one thing we know for sure is that the caterpillar is what dominates the norm of the state on average. So because we can do the CFT computation, and it turns out that the bulk saddle point computes that thing well. Another question is other observables, like the two-point function. For the two-point function, what happens is that the computation at the disk level is subdominant after some time because the wormhole becomes too long, at least on average. And so even in this case, it's not clear to me where the exponentially small signal comes from. A possibility is that it could come from the caterpillar. So you could start with a distribution of matter, which is very erratic, and somehow when you try to compute the two-point function, the two-point function factorizes, and so this end of the two-point function is contracted with some matter insertion inside of the caterpillar, but close to the horizon, and so you end up having like a non-zero signal, which could be erratic and exponentially small. That's a possibility, but yeah, I think it is an open problem. We haven't figured that out.
But I guess my question was more specific. If it's true, as you say, that probably you need a wormhole of length S to get this kind of behavior, do you have a reason to believe that the physics of that wormhole is in fact semi-classical?
Well, yeah, I guess.
Or might it involve a
so
large
you're saying there could be like 1/s corrections to our calculations that when the wormhole is over S, they become important and something.
Yeah, again, the extreme black hole seems like a good paradigm. As you lower the temperature and the throat gets longer, you find more and more relevant strongly coupled modes, and at a certain level you can study it with the Schwarzian, but if you go too cold, it goes out of control even at that level.
It could be, yeah. I don't have a proof that these corrections are not there. What I would say is that, well, I personally think that, well, 1/s corrections, like the same happens for the evaporating black holes. They don't seem to spoil anything, at least,
That we could talk about more.
Yeah, let's talk about it more.
Another question? Okay, if not, let's thank Martin again. Let's